All right, we'll go ahead and get started. First off, I want to thank everyone for joining this current iteration of our SPTC webinar. My name is Michael Molina. I'm the Workforce Development Coordinator for SPTC. And before we get started, I'm going to go through a few ground rules that will follow during this presentation, and then we'll proceed into the presentation and have a question and answer session afterwards. So for starters, please make sure you are muted upon entering. We don't want any external audio to interfere with our speaker today. So make sure and keep yourself muted. And if you would like to ask a question, you can raise your hand at the end of the presentation and unmute yourself, or you can type in the chat box and we can read off your question to our presenter. Also, if you attend for the full hour, you'll get 1 hour of PDH. We'll send that out to everyone via email afterwards. And we'll also send out a survey so you can let us know if you have any thoughts about the presentation or if you'd like to see any other new topics that you would like us to cover in a future iteration of the webinar series. So with that said, I'd like to provide a brief introduction to our speaker. His name is Dr. Mostafa El-Saifi. He is the Occidental Chemical Corporation Distinguished Professor at the Department of Civil and Environmental Engineering at Louisiana State University. So he'll be presenting on performance evaluation of OGFC mixes with waste plastic, reclaimed asphalt pavement, and steel slag. With that said, I would like to turn it over to Dr. El-Saifi. Oh, and it looks like you're muted.
All right, thank you, everyone. Let's go ahead and start the presentation. So this project was funded by the Southern Plain Transportation Center. We have just completed the research work, so many of this work has not been published yet. To start with a little bit of introduction, OGFC has been around for quite some time. It has many functional benefits for the user. It drains the water very quickly, and it also reduces the noise from traffic. It improves the friction at the surface. It reduces the risk of hydroplaning. So many functional benefits for the user. However, in terms of performance, it does not last as long as regular dense graded hot mix asphalt. And the reason is that we have a very high air void content. This air void content reduces the film thickness of the binder, which leads to premature raveling and stripping of the mix. Also, the high air void, even though it works very well at the beginning, they tend to be clogged with dust and debris over time, which may reduce the permeability of the mix. So these are some pictures they were taking in Louisiana. You can see the benefit of OGFC in reducing splashing and hydroplaning, especially in the event of heavy rain, which we have very frequent in Region 6. Also, another study have looked at the amount of accident rates. You can see OGFC, which is shown in green, has a much less accident rate than regular mix. So that's also an added benefit of this mix. In terms of durability, these are examples of raveling of the mix. It's usually constructed with a very thin thickness, which again makes it very susceptible to raveling. We also have seen in the literature early top-down cracking from this mix. So it has a lot of performance issue, and we cannot really argue about that. In terms of reduction of noise, this study was done in Nevada. You can see the very clear reduction in noise, which again is a very important issue, especially in urban area. As I said, the cost of OGFC is higher than dense graded. So again, this is mostly due to the higher asphalt content. And again, this is also an issue that we are going to discuss in this presentation. In terms of construction, again, the mix is very thin, and you can end up with some problem after construction. Again, this requires a very skilled contractor that have experience in constructing and compacting this type of mix. And again, the reduced permeability was looked at in the literature. You can see it does decrease over time. So mostly due to debris and dust in the air void, and also because of the consolidation that happens to the mix over time. So our objective was to look at innovative method to reduce the cost while improving the performance of this mix. So we looked at the incorporation of recycled plastic waste, reclaimed asphalt pavement, and steel slag. We also looked at the use of high polymer modified asphalt binder and hydrated lime that we use as slurry in the mix. So again, as part of our state here, and I'm sure other states in the region, none of these additives are currently allowed or are used in OGFC. Then we looked at the cost effectiveness. So after we assessed the performance, we looked at the cost effectiveness, which again is a very important issue when dealing with mixed production and construction. And we also looked at, because it has been claimed that OGFC can degrade pollutants. So when you get pollutants in the mix, can it help degrade these pollutants? For example, when you have motor oil on the surface, can OGFC help with this type of contamination? And I'm going to show you the results. So the results methodology, we started with a literature review, which again, I'm not going to present here because of the time constraint. Then we selected the material, and this again was based on a wide range of attempts. So I'm just going to show you the final product. Then we designed and prepared the mix. We did the laboratory testing. Then we did the performance analysis of the results, and we also did the cost analysis. So the mix that we used was provided by the Louisiana Department of Transportation and Development. This is a mix that is actually approved by the department, and it has been used in roads. So it's a mix that, again, has been designed and has been approved. So some of the features that I'm highlighting in red, it's the nominal maximum aggregate size is 12.5, which what we use currently in the state. We have two sources of aggregate, so it's a very simple mix design, but it meets the specification. We use PG7622, which is a polymer modified at 6.5% content. We have fiber to reduce drain down. We also use Dicoserm, which is anti-stripping agent, and it also has some other benefits for the mix. And you can see that the air void of the control mix was 22.6. So again, in Louisiana, we require an air void of 18 to 24, which is again tremendously high compared to dense graded hot mix asphalt. So the additives that we use, so we used recycled plastic waste. You can see it in the picture here. It's a high density polyethylene, and we replaced it with at a content of 3.75 of the total weight of the dry aggregate, which again, in OGFC, this has not been attempted before, so it was something new for us. The reclaimed asphalt pavement, or RAP, you can see it in the picture here. We use at a content of 7%, and we also use steel slag at 7% of the dry aggregate. We also did the differential scanning calorimetry to look at the melting point of the plastic, and it was around 167 degrees Celsius, as you can see from the blue peak at the bottom here. For slurry, we used it as the hydrated lime. We used it as a slurry, which again is the preferred method to incorporate hydrated lime. So we mixed it with water at a ratio of 1:2, and then we blended with the dry aggregate, as you can see in the picture at the bottom. And after the aggregate are adequately coated with the hydrated lime, we placed it in the oven overnight at 110 degrees Celsius. In terms of the high polymer modified, so again, this was started with a base binder of PG5828, and it was modified with polymer at 7.5%. So that's it's higher than PG7622, but again, this binder is slightly more expensive than PG7622, but we are going to look at the cost at the end of the presentation. As I said, Zycosert is a very effective anti-stripping agent that we added to all type of mix. Again, in Louisiana, we have the second largest rainfall in the United States after Hawaii. So you can imagine how much rain we are getting. So again, it's very important to use anti-stripping in all our mix. These are the 6 mixes that we have in the factorial. So CM stands for control mix, and then the RAP, which incorporated RAP, 7% RAP. SS means steel slag. RWP means recycled waste plastic. HL means hydrated lime, and HiMA means high polymer modified asphalt. So these are the 6 mix that we incorporated in our test factorial. So the tests that we did, some of them are volumetric. So we measured the air void, we measured the permeability of the mix based on the Florida DOT test method. And the minimum requirement, so there was a large NCHRP that was conducted 1/55, and it recommended a minimum permeability of 164 feet per day. The drain down was conducted to assess how much asphalt will drain during the production. We looked at the compaction energy index, which is a method to assess how much compaction effort you would need during the mix compaction. So that's a very important factor in terms of how much fuel you will consume and how much time you will need to achieve the desired air void. In terms of performance, we conducted the Contabro aberration test, which is a very important test to look at the raveling resistance of OGFC. We conducted the rutting test based on the Hamburg wheel tracking test. We conducted the ideal CT to look at the cracking resistance of the mix. And we conducted the modified Lockman test to look at the moisture resistance of the mix. So again, these 4 tests really give you a comprehensive assessment of the performance of the mix. And again, that's very important. So the Contabro abrasion test is a test that was highly recommended for OGFC because it is very prone to raveling, and it really subjects the mix to a significant effort to cause raveling, and it provides a very clear assessment of this failure mechanism. So the way it's conducted is that you place your specimen in the LA aberration drum, which is shown here, and you place it without the steel balls. So that's a small modification. And then you conduct the test for 10 minutes, and you measure how much aggregate or how much mix loss you had at the end of the test. And again, this test is a very important test to assess OGFC mix. The compaction energy index is measured based on the gyratory compactor. Is that we plot the percentage GMM versus number of gyration, and then we calculate the area under the curve, and this will give you how much compaction effort you should expect during the compaction of your mix in the film. The Hamburg wheel tracking test was conducted using H2T 324. And again, for OGFC, because it has high air void, the state here requires to measure the rub depth after 5,000 passes. But NCHRP recommend to look at the rub depth after 20,000 passes. So we looked at both rub depths and we compared them between the different mixes. For the ideal CT, so it consists of loading the specimen on the apparatus shown here, and you create this plot of load versus displacement, and then you calculate something called the CT index. And again, the CT index is an indication of how much energy you will exert or how much energy you will apply to get the specimen to failure. And again, this is a relatively new test that has been introduced in Texas. And the CT index, there is no really national value or threshold to assess the CT index until now. But VDOT use 100 for the CT index. Other states use a slightly lower value, but again, this is the value that we use in our evaluation. The tensile strength ratio or the modified allotment test consists of testing 3 specimens conditioned and unconditioned. And then you calculate or you measure the indirect tensile strength of the unconditioned and the conditioned. And the ratio of strength between the two gives you an indication of the moisture damage resistance of the mix. So for OGFC, NCHRP 155 recommended a TSR of 0.7. For in ASTM, they recommend a TSR of 0.8. The state here in Louisiana doesn't use the TSR for OGFC, it uses the boiling test. But again, this test that I'm showing here is more scientific, and that's why we use it in our assessment. And we aim to achieve a TSR of 0.8 for our mix. The final test that we did is called the bitumen bond strength. So we wanted to look at the effect of the different binder and the different fillers obtained from these different modifications that we did on the strength between the mastic and the aggregate. So it consists of mixing the binder with filler. Then you pour it in a DSR silicone mold. And after that, you place your sample at the bottom here of the stub. And then you push it on an aggregate sample that I'm showing here. And then you pull it at a loading rate of 150 psi per second. And you measure the pull-up tensile strength. So this test is done under dry condition and after wet conditioning. So the wet conditioning consists of submerging the specimen in distilled water at 40 degrees C for 24 hours. So we measure the loss of bond between the dry and the wet. And again, it gives us an assessment of the strength between the mastic and the aggregate. And again, it's a very important property that relates to the adhesion strength that is achieved in the mix. So before I show you the results, let me show you how we are presenting it, is that we did a statistical analysis of the results. We use an ANOVA analysis at 95% confidence. And the hypothesis, the null hypothesis, is that there is no statistical significant difference between the different mixes. And again, the way we are presenting the results is that we also did a Tukey honest significant difference, HSD, at a 95% confidence level. And I'm going to show you the results. So if you see the same letter on two mixes, that means that these mixes are statistically equivalent. If you see different letters, for example, A and B, that means that the mixes are statistically significantly different. And again, that's a very important process because you don't want to just look at the results and try to use your engineering sense to assess the difference. So a statistical assessment is much more useful. Is that again, if you see differences if you see different letters, that means that the results are different. And we tend to put the letter A for the best performance, B for the second, and C for the less, and so on. So before we get to the results, let me show you how we did the cost-effective analysis. So this is a very important part because, again, looking at the cost only, in my opinion, can be highly misleading. So to calculate the cost effectiveness, you can see it here, it's equal to the effectiveness, E, divided by the cost. So the higher this ratio, the more cost effective your mix is. So to determine the cost, we obtained the cost from different sources, from contractor, from the DOT, and again, mostly from Louisiana region, but also from the region 6 in general. And the expected performance, you can see it at the bottom here. So we combined the four performance that we have. So you have the CT index of the mix divided by CT maximum, and the rod depth, and the Contabro loss, and the TSR. And all of these will give you the effectiveness of the mix. So again, this method is relatively simple, but in my opinion, it's very accurate because you have the performance and you have the cost of the mix in one ratio. To look at the biodegradation, we basically what we did, we had a dense graded and we have an OGFC specimen. So we subjected them to two types of contaminants. We subjected them to heavy metals, which included lead, copper, zinc, and cadmium. And we subjected them to motor oil. So we used EPA method 160.2 to assess how much biodegradation you will get in the specimen when you pass these contaminants through the specimen. So again, you have this filtration process and you have the biodegradation. And again, the good thing about OGFC is that you have this high storage capacity of contaminants, and that allow the biodegradation of these pollutants. And I'm going to show you the results. All right, so showing you the results of our investigation. The air void of the different mix, again, what I'm showing here, we have the 6 mix, and we defined the abbreviation before. So CM means control mix, SS means steel slag, RWP means recycled waste plastic, RAP, reclaimed asphalt pavement, HiMA, high polymer modified asphalt, and HL means hydrated lime. So in terms of air void, we want to achieve between 18% and 24%. So anything in this range is acceptable from a specification point of view. The blue line is what is recommended by NCHRP 155. So again, you can see that all our mixes satisfied this range, as it is important to do because you want your mix to be comparable. If we look at the permeability, so the permeability is directly related to the air void. So you can see here that HiMA and hydrated lime had the lowest permeability, but again, it's higher than the minimum requirement. And the other mixes, you can see CM, steel slag, and RAP had statistically equivalent. And the recycled waste plastic also had within between the two groups.
Go and do more granular analysis with some of those.
As a reminder, please keep yourself muted. Thank you.
All right. So the drain down, as you can see from this slide, was not an issue. We had fiber, so that really helped. So again, the maximum drain down that we wanted was 0.3%. You can see that all the mixes were less than 0.1. So that's also very good news. The compaction energy index, again, showed us very interesting results. So the control mixture had the highest compaction requirement, which is again shown here on the left. So it had this C grouping. In contrast, the hydrated lime, followed by the HiMA and the RAP, had the lowest compaction energy requirement. So again, why this is the case? So again, this relates to the viscosity of the binder. And again, you can see that it's possible that hydrated lime facilitates the compaction process, and that's why it had the lowest compaction energy requirement. In terms of the Contablo, and this is the first mechanistic test that we did, you can see that there is a very significant difference. We have two main groupings. We have the RAP and the HiMA had a very low abrasion loss. And on the other hand, we had the CM, the steel slag, the recycled waste plastic, and the hydrated lime in the second grouping, which was above the 20% recommended by NCHRP. So you can see that we have two significant difference between these different mixes. If we look at the rutting, you can see that at 5,000 passes, all the mixes passed, which is the top figure here. You can see that all of them had a rod depth less than 12.5 millimeters. However, at 20,000 passes, you can see that we started seeing difference between the mix. And again, the control mix and the RAP mix had the highest rutting. On the other hand, the steel slag and the hydrated lime had the lowest rutting. And in between, we had the recycled waste plastic and the HiMA, which was below the 12.5 millimeter. So it means that they passed this factor. So again, keep in mind the control mix is the one that we use. So obviously, if we have inferior durability of this mix, we have seen that we have two performance factors that were not met by this mix, which was the Contablo loss and the rutting at 20,000 passes. And these are the different rut curves. So again, rutting curves. So you can see that most of the mix performed in the region 2 of the creep curve, so they did not get to the tertiary region. However, you can see that the control mix and the RAP had higher rutting than the other mix. And again, the RAP was kind of a surprise for us, but it's possible that this RAP source had a polymer sources in it, or it had some damage during field utilization. So again, and the RAP content that we use is only 7%. So it's possible that at this low content, you don't see a very significant drop in rutting when you use RAP. In terms of the cracking resistance, you can see here, so the higher the CT index, the better. And we had three groups. So we had the hydrated lime and the HiMA as the best performance, which are shown on the right. Then we had the RAP, the recycling waste plastic, and the steel slag, the second best performer group. And then the control mix was the lowest performing group. So again, that indicates that the control mix that we use in real life will not perform as well as the other type of additives that we considered in this study. Finally, the TSR, you can see that we set a threshold of 0.8 to be on the conservative side. So you can see that all the mix met this 0.8 with the hydrated lime and the recycling waste plastic slightly better than the RAP and the HiMA and the steel slag. And again, the control mix was statistically grouped as the worst performer, as Group C. In terms of the bitumen bond strength, we found that the highest strength was obtained for the HiMA mix. You can see it here. And we have two columns because one of them is the dry and one of them is the wet. And the second best performance was the RAP and the hydrated lime in terms of bond strength, followed by the recycling waste plastic and the control mix, and the steel slag was the lowest performer. So again, it's possible it's due to the nature of steel slag, which is again slightly different material than the other type, which may affect the adhesion strength between the binder and the aggregate. In terms of bond strength, the best performance was the HiMA, so it did not lose that less than 10% loss after conditioning, followed by the RAP and the hydrated lime. And then the third group was the control mix, the steel slag, and the recycled waste plastic. So this slide is in my opinion, is the best, most important slide. So again, we said that the cost of HiMA was slightly more than the PG7622, but when we looked at the performance as compared to the cost, the best two performance were the HiMA and the RAP mix. And again, this accounts for both the cost of the mix and its performance. It was followed by hydrated lime and steel slag, then recycled waste plastic, and finally the most costly mix when you look at the performance is the control mix. So again, looking at the initial cost is highly misleading. So the control mix may be cheaper than other type of mix, but when you look at the performance, it's actually more expensive. In terms of biodegradation, so what I'm showing at the top here is the degradation of these four contaminants or the four metals, lead, copper, zinc, and cadmium. And we found that OGFC is very efficient in degrading or removing zinc and copper. So it was very, you can see here the concentration of the pollutant over time. And you can see that the zinc started at 100%, and at the end of the experiment, it was less than 20%. So again, we have very significant removal of zinc from OGFC. The bottom two shows you the degradation of motor oil. So motor oil can end up on the surface very easily during traffic and other type of vehicle maneuvering. And you can see at the bottom here, when we compare the amount of oil that has been filtered, we can see that OGFC is able to filter motor oil much more significantly than the control sample. So again, that's an added benefit of OGFC that is not really considered in pavement engineering. So this slide summarizes the performance measures that I showed you. So the green highlights the best performance, and the pink highlights the worst performance. So we can see that there is a trend. Usually the HiMA is the best performer, and the control mix is usually the worst performance. Obviously, there are some deviation in some of them, but again, this is the general trend. In terms of cost effectiveness, the HiMA was the best performance, followed by the RAP. So again, RAP is usually is not considered in OGFC in Louisiana and other states. So again, this is something that is worth looking at, because when you talk to compactor, they always tell you OGFC is very expensive, and that's a major challenge. So in conclusion, we found that the incorporation of HiMA, RAP, and hydrated lime significantly improve the raveling resistance of the mix. Also, the hydrated lime and HiMA achieve the highest cracking resistance for the mix. All the mix met the rutting criteria at 20,000 parts except the RAP and the control mix. And the mix with highly modified asphalt binder and RAP was the most cost effective. You can see there was a very clear distinction in cost effectiveness. And the mix with recycled waste plastic performed equivalently or slightly better than the control mix. So again, if that's something that is worth considering for environmental reasons, we found that the mix with recycled waste plastic performed slightly better than the control mix. So in terms of recommendation, we think that we have good confidence in incorporating RAP, recycled waste plastic, hydrated lime, and HiMA and OGFC. And we think that the next step would be the field performance evaluation. So to build some test section and to look at the field performance of these mixes and see how it goes. And again, if it confirms our laboratory results, that's a very positive sign. We also would like to look at different percentage for these additives. So this is something that we did not look at, and it's worth considering in the future. We also should conduct an environmental impact analysis to look at the environmental benefit of these different additives. And if we are able to do the field performance evaluation, we should associate it with a cost-benefit analysis. So we can also get more accurate cost evaluation of these different type of mixes. So in conclusion, as an acknowledgement, I would like to thank the Southern Plains Transportation Center for funding this research. I would also like to thank Paragon Technical Service for helping us with the Contabro test. And I would like to thank Mr. Sean Maher and Barry Moore of the Louisiana Department of Transportation. They helped us with our study. And Mr. Don Weather, who is in Louisiana, for helping us, especially for locating the steel slag for this study. So with that, I would like to answer any questions that you may have.
All right. Thank you so much, Dr. El-Saifi. That was an excellent presentation. And we do have a few questions that popped up. If you would like to ask a question, please feel free to type it into the chat box, or you can raise your hand and unmute yourself and ask your question directly. So I'll go ahead and read off a few of the questions in the chat box while we wait. First question is, could you clarify the role of recycled plastic in view of its melting temperature?
Yes, that's a very good point. So we were worried about the melting of the plastic, but we did not see any problem with that for two main reasons. Is that we used a relatively small amount compared to the body of aggregate that we had in the mix. So we blended it with the aggregate, and then when you heat it for 2 hours, because of the large quantity of aggregate compared to the plastic, we did not have any issue with the melting of the plastic.
All right, and next question is, voids in OGFC mixes can get clogged with time due to dust, debris, and other reasons. Your previous studies mentioned using biodegradable materials to open clogged voids or pores. How would your lab-based results relate to field performance?
So this is an issue that is obviously quite important. And you have to keep in mind that there are major challenges with the performance of OGFC. Like in the field, you can end up with problem maybe after 3 years or something like this. So if we are not able to fix the performance, the clogging of the voids will be a secondary issue, because if you have raveling or if you have cracking, your voids are completely destroyed. So you would not have clogging of the void because basically you lost the structure of your mix. So the entire structure, and keep in mind that they tend to use OGFC for a thickness of 1 inch or maybe 3/4 of an inch. So these are very thin layers. And if they do not perform up to standard, your mix will be destroyed very quickly. And then your air voids basically will be susceptible to the environment. You don't have a real mix at the surface. And you can see this problem like if you go to Florida or if you maybe here in Louisiana, when you drive on OGFC, you always see raveling again. So that's a major issue. And again, some states tend to use a lot of OGFC. Here in Louisiana, you feel like the interest had went up and now it's going down again. So again, the DOT always want to optimize their funds. And if they know that OGFC will last for 3 to 5 years, they will probably not use it. And that's a challenge that we have. So even though the functional benefits are tremendous and in my opinion are really good, this is something that we need to address so we don't fix a problem and end up with another. And that's what we are currently with this type of mixes.
All right. And next question is, are all 4 of the tests of equal importance in performance?
And this is a good point. So again, I would think that raveling is probably the most important one. And you can see that we have if I go back to this slide, if we see the raveling here, you can see that RAP and HiMA had a exceptional performance compared to the other mixes. So this is probably the most important test, followed by the ideal CT. And that's, again, because the cracking susceptibility of the mix is very high.
Right. We have one last question. In Oklahoma versus the wet climate of Louisiana, would it be better to study fly ash instead of hydrated lime as an additive?
So that's a good point. I think fly ash, the concrete industry is using a significant portion of it. So I think there is a type E and type F, and I think type F is a good one. And we were actually sometimes when we try to use fly ash in our research, we have problem finding it because it seems the concrete industry is using most of it. So even though fly ash is a byproduct, so it would be more environmentally friendly. And again, you should expect similar result, but maybe slightly inferior than hydrated lime. So hydrated lime has a very high strength activity index. That's something that allows us to create this slurry and get this very strong adhesion. Fly ash, I would expect it to perform similarly, but again, the availability of the byproduct and also slightly inferior stress activity index than hydrated lime.
All right, thank you. That's it for questions posted in the chat. I'd like to give another minute to any of our audience members who would like to either type out a question, or if you have a question and would like to unmute and ask directly, you're more than welcome to do so at this moment.
Hi, Dr. El-Saifi. Thank you very much for the nice presentation. Can you hear me?
Yes.
Okay. Yes, I have one question. Is about the cracking resistance of asphalt of the mixes, OGFC mixes. So generally, we have seen when we add wrap or recycled plastic, we have seen problem with the cracking, especially the CT index value. So, but here we are seeing some increase in the cracking resistance. So, is there any specific reason for that? Do you have any kind of explanation for? for that? Thank you.
So, thank you for your question. So I think that it's possible because the RAP percentage was slightly lower than what is currently used for other type of mix. So if we go back to so the RAP percentage is was only 7%. So again, that's a factor to consider. And recycling waste plastic, it also depends on the source of plastic that you use. So again, we have, and again, like I know that the majority of studies that do recycling waste plastic, what they do is that they grind the plastic to maybe filler size, and also they mix it with the binder. And again, this is a completely different approach. So if you mix it with the binder, then you end up changing the rheology of the binder. So if you look at the flexibility of your binder, and based on my experience, plastic, it's possible that it will react with the binder, but I would think that it most probably will act as a filler in the binder. So if it acts as a filler, meaning that similar to filler aggregate, you will not get any improvement in flexibility, because asphalt binder, and again, we have some experts of binders that are more experienced than me, but if you look at the binder, it has a very high resistance for reaction. Like in my previous studies, when you mix binder, for example, with shingle or with other type of additives, it doesn't react easily. And if you end up with a filler, it may affect the flexibility of your binder, which may reduce your CT index. So again, most of the study, when they use plastic, they want to grind it to passing 200, and again, that will increase the cost tremendously of the mix. And at the same time, they want to blend it with the binder, and then use the blend in the mix. And again, that's, in my opinion, that may not be the best approach. Why? Because first, the amount of plastic that you can use is minimal, so you don't really solve any problem. And at the same time, you may end up negatively affecting the flexibility and the rheology property of your binders. So again, what we did here is different, is that we did not grind the binder, we used it to replace part of the aggregate, so it was actually a larger piece. So we determined the particle size of the plastic, then we removed the same aggregate with the same size, and we replaced it with plastic. So in that case, we don't affect the binder in any way. So we found some benefit in doing that. And again, that's something that I know that you guys are doing a lot of work in plastic, and that's something that you guys may consider, is that instead of grinding your plastic, consider adding it as a replacement for the dry aggregate. And that will allow you to use more plastic in your mix. And that's, in my opinion, that's exactly what we are trying to do. We are trying to address the landfilling of waste plastic by using it in the mix. So if you can use more, it will help us addressing this issue.
All right, and we had one more chat. One
Mm.
more question popped up in the chat. What size was the recycled plastic in your study?
I want to say it was a 3/8 of an inch, but I may have to check. But again, the final report has been just submitted. You guys are the first researcher to see this results, actually. So it has not been published. It's fresh from the oven, I guess. So the final report, you should expect it very soon. And if you check the SPTC website, maybe in a month, you will find the final report, and it will have all of the details that I presented today.
All right, last call for questions. Any final questions or comments anyone would like to share? All right. If not, I'd like to give a big round of applause to Dr. El Saifi. That was a great presentation. Thank you so much. We have this recorded and we'll post this on our website probably by next week. If you had registered for professional development hours, we will also send those out within a week or two as well. And do be on the lookout for a survey we'll send out. Please let us know how we did, what you'd like to see in the future. And your responses and comments are always very appreciated and helpful, so we can make our presentations and this workshop series the best it can be. So with that, again, thank you so much, everyone, for participating. A big thank you to our guest speaker, and we look forward to seeing you during one of our next webinars. So thanks again, everyone.
Thank you.